Imagine a world where gravity is perfectly uniform. But on Earth, gravity varies by up to 0.5%, creating invisible bumps and dips that shape our planet. These tiny differences reveal huge secrets. These are gravity anomalies, measured in milligaules. 1 milligoule is a millionth of Earth's gravity. Yet these tiny differences reveal hidden oceans and the planet's core. So why is gravity weaker in certain spots? The answer lies deep within Earth. We'll explore the most dramatic anomalies, from Hudson Bay to a giant dent in the Indian Ocean. Ever wonder why gravity isn't the same everywhere? That's a gravity anomaly, the difference between expected gravity and measured gravity. These tiny variations reveal hidden structures beneath Earth's surface. We need a reference, the geoid. It's the shape the ocean would take under gravity and rotation. But Earth's gravity isn't uniform, so the geoid has bumps and dips, up to 200 meters of variation. 1 milligoule equals a millionth of Earth's gravity. Satellites like GRACE detect differences as small as 1 milligoule. This reveals startling features. Hudson Bay, where gravity is 40 milligaules weaker. Why is gravity weaker in Hudson Bay? Post-glacial rebound. A massive ice sheet pressed down, compressing the crust. Now the ice has melted, and the land is slowly rebounding. This rebound is still happening. The crust rises about 1 centimeter per year. As it lifts, mass distribution changes, causing a gravitational deficit of -40 milligaules. 1 milligoule is a millionth of Earth's gravity, so -40 milligaules means gravity is 0.004% weaker, tiny but measurable, and it reveals hidden dynamics. But is rebound the whole story? No. The anomaly is larger than rebound alone can explain. Something deeper, a mantle plume or compositional differences, is pulling gravity down. What's the biggest gravity hole on Earth? South of India, the geoid dips 100 meters, the Indian Ocean geoid low. It's the most dramatic anomaly of all. The answer lies deep beneath the ocean floor. A massive plume of hot, low-density rock rises from the mantle, creating a gravitational deficit and pulling the geoid downward. This plume, the African Large Low Shear Velocity Province, extends thousands of kilometers upward. Its low density reduces gravity by up to 40 milligaules, creating the geoid's deepest depression. Here's the twist. This same plume that causes the gravity hole also fuels volcanic hotspots and drives tectonic forces. Gravity anomalies are windows into Earth's dynamic engine. So, what causes the extra gravity loss in Hudson Bay? The mantle. As the crust rebounds, hot, less dense mantle rock flows upward, creating a persistent gravitational deficit. Far south of India, the Indian Ocean geoid low marks the largest gravity anomaly, a 100-meter dip. A massive plume of hot, buoyant rock rises from the mantle, thinning the crust and reducing gravity. These anomalies are windows into Earth's dynamic interior. The same mantle plumes that create gravity dips also drive plate tectonics and volcanism. By mapping gravity, we see the hidden engine that shapes our planet. How do we map these variations? Satellites like GRACE and GOES measure gravitational pull with astonishing precision, detecting changes as small as a single milligoule, and they track changes over time. GRACE, launched in 2002, measures gravity by tracking distance between two satellites. As they orbit, local gravity pulls them closer or apart. This reveals dynamic changes, like 2.5 centimeters of groundwater loss per year in some aquifers. GOES measured gravity gradients directly from a low orbit of 200 km. This gave the sharpest picture of the geoid, revealing that massive dip south of India in stunning detail. These maps are essential for sea level rise and GPS. These maps are essential for accurate sea level rise measurements. Without correcting for gravity's bumps, satellite altimeters would misinterpret a 1 milligal anomaly as a 2-centimeter change in sea height. But how do we actually map these anomalies? The GRACE mission uses 2 satellites following each other in orbit. As the leading satellite passes over a gravity anomaly, it speeds up or slows down, changing the distance between them. This distance change is measured with micrometer precision. Over time, GRACE builds a global gravity map every 30 days. It can detect changes as small as 1 milligal, revealing groundwater depletion and ice melt. Then came GO-SEA, flying at just 200 kilometers altitude. Its gradiometer measured gravity gradients directly, giving the sharpest geoid map ever. It revealed the deepest geoid depression in stunning detail. These maps are crucial for sea level rise. Satellite altimeters measure ocean height, but gravity anomalies distort the reading. A 1 milligal error translates to a 2-centimeter sea level error. Correcting for the geoid is essential. GPS also depends on a precise geoid. Your phone calculates position relative to Earth's center. If gravity is uneven, that center shifts slightly. Without a correct geoid model, your location could be off by meters. GRACE also tracks changes over time. In California's Central Valley, it detected groundwater loss of 2.5 centimeters per year. Gravity anomalies become a time machine for water resources, revealing hidden depletion. In Greenland, GRACE measured ice loss of 200 gigatons per year. As ice melts, gravity decreases. These measurements confirm climate models and show that gravity anomalies are not static. They evolve with our planet. But the biggest anomalies come from deep Earth. Seismic tomography reveals massive plumes of hot rock rising from the core mantle boundary. These plumes are less dense, so they reduce gravity above them. The largest plume is the African Large Low Shear Velocity Province. It stretches thousands of kilometers upward. This plume is responsible for the biggest gravity hole on Earth, the one south of India. This same plume fuels volcanic hotspots like those in Hawaii and Iceland. As the plume rises, it melts to form magma. So the gravity hole is linked to surface volcanism, a direct connection between deep Earth and our world. Gravity anomalies also drive plate tectonics. The pull of gravity on dense, cold slabs at subduction zones helps move plates, so the same variations that create bumps and dips also power Earth's engine. Future missions like GRACE-4 and MAGIC will measure gravity with even higher resolution. They'll track changes in ice sheets, groundwater, and sea level. Each new map reveals more of Earth's hidden dynamics. So the Hudson Bay anomaly is a combination of 2 effects: the slow rebound of the crust and the inflow of hot mantle rock. Together, they create a persistent gravity low that will take thousands of years to fade. But these anomalies aren't just local curiosities. A global gravity map reveals a pattern. Gravity is slightly weaker over oceans and stronger over continents. This reflects the thickness and density of the crust. Over the ocean, gravity anomalies reveal seafloor features like trenches and mid-ocean ridges. The Mariana Trench, for example, has a positive anomaly because dense crust is pulled deep into the mantle. Hotspots like Hawaii also show gravity anomalies. As the Pacific Plate moves over a mantle plume, a chain of volcanoes forms. Gravity maps reveal the plume's path and the thickening of the crust. From Hudson Bay to the Indian Ocean, gravity anomalies are fingerprints of Earth's dynamic interior. They show us mantle convection, plate movements, and even water cycles. Gravity is never wrong. It's telling us exactly what's happening below. And GPS depends on a precise GEOAD model. Your phone's location is calculated relative to Earth's center, but if gravity isn't uniform, that center shifts. So next time your GPS guides you home, remember, it's navigating a planet with hidden variations, a world where gravity is never quite what it seems.